But what we're after now is that we now want to go into Newton's laws for a system of particles. A system of particles.
Hey, Carlos.
This is where it's the most interesting. Yes.
When you say the center of mass is below the bar, from the picture, that kind of looks confusing because it, like his body is above the bar.
Well, like one of the things that I was saying here is that I tried to get a clip where he essentially is part of his body is below you. It's almost like his body's folding like this. Obviously, he can't fold like that, but what you would find here is that right in here, what you would see here is that his head and upper body are actually folded down and his legs are over here.
I got it. Yeah. So totally. It makes sense now. Thank you.
Okay. So this piece here is why I think center of mass is such an awesome, concept. And it's because what it means when you apply Newton's laws. And Newton's laws is everything that we've been talking about up to this point. So here we go. Okay. So what we need here is that we need a system of particles that we have a closed system of particles. So we assume a closed system of particles. And what that means here is that what it really means here is that when we're talking about the total mass of the particles, however many they are, that this is a constant of the system. And so when I'm thinking about this closed system of particles here, I imagine that I have something like this here. Here's my system, right? And now what I find here is I have a system of interacting particles. So that means I have a particle going like this, maybe like this, however they're moving here. And I could call this 1, 2, 3, n. And what I'm going to do here is that as I look at these particles, there's something super distinct about these particles. Somewhere, some location here is going to be the center of mass. And what that center of mass does here is that it tells us how the system behaves.
Hey,
Okay?
Carlos, since the
Yeah.
particles are moving, would the center of mass change at all?
Say that one more time.
Since the particles are moving around inside the system, would the center of mass change at all?
Not if they're random. And you'll see that that's one of the things that we're actually going to go after. Okay? So here we go. Why is the center of mass important? And the answer is that it allows us. So let me ask you this question that you just asked. What about the center of mass of the Earth? Would you say that's fixed? But doesn't the wind, the ocean, and all the things that are moving around in the Earth, those vary? But if it's an isolated system, the center of mass is fixed on that. The sun is even worse. The sun actually moves quite radically within its boundaries. But I bet you would say that the center of mass of the sun is a fixed quantity. Okay, it allows us to what? track the center of mass location. And what I mean by the center of mass location, I want the center of mass location, the velocity center of mass, the acceleration, and then of course, the system of the force, the net force. So let's go do some very, very, very basic definitions. Okay, so here are some basic definitions. So the first thing that we want to do here is that we want to start with position and get the velocity center of mass, right? So we're going to go from our center of mass to velocity center of mass. And what we're doing here is that if you look at this thing here, we imagine that we have our center of mass should have 2 points in 2 dimensions. So you could imagine then, if I then start with this guy, we should be able to take the derivative of this quantity. But if I take the derivative of this quantity, then my system should be, and then it should be the sum of the locations of all of the masses here. But wait, the total mass is a constant, so are the individual masses. So I could slide that little guy right in. And if I slide this little guy in here, then what I'm really seeing is that I'm seeing what? The derivative of the center of mass. And this gives us one of the most important concepts in all of science right here. That this term right here is then the individual velocities, and this is the term as V center of mass. And this is one of the highlights of this whole chapter right here. That little equation, man, that little dude is powerful. Super, super powerful. And then you could imagine that I could do another, another simple basic definition. I can go from V center of mass to the acceleration center of mass. And you could imagine what I'm going to do. I'm going to take the derivative of this guy. So if I do that, I start off by taking the derivative of the center of mass. But if I take the derivative of the center of mass, if we just move a little bit faster, we know that all the mass terms are a constant. So then I'm really taking the derivative of what? All of the individual velocities. And so then we define a new expression. And we say, wait, let me be careful. What I mean by that is that I haven't defined it yet. I jumped the gun a little bit. But now I have all of the individual accelerations multiplied by the mass. We then define a new quantity called the acceleration of the center of mass. And so it makes sense here that if I have a closed system, that I can define these constants.